So let us see now how to modify our previous algorithm for matrix chain multiplication such that the time complexity comes down from exponential to polynomial. So this is the dynamic programming approach now. So far we have just seen how bad it can be without any clever trick. So what I will do first, I will write down the algorithm for you, okay. Then I will explain what it is doing. So let me first write down the algorithm. Again its input is the array P for I is equal to 1 to n do m I, and suddenly you can see previously this m was a function call. Now we are replacing this entire function call by a matrix. It's a two-dimensional array. I told you already that the intermediate results we need to keep somewhere so that we can use it again and again. So for keeping intermediate results we use a two-dimensional array where we keep all the results. This is the bookkeeping we are doing. So this is the initialization, this part, and for L is equal to 2 to n do for I is equal to 1 to n minus L plus 1 do j is equal to I plus L minus 1 m ij equal to plus infinity for k is equal to I to j minus 1 do mult m I k plus m k plus 1 j plus p I minus 1 star pk star pj if mult is less than m of ij, then mij is equal to mult, and I'll tell you later this what this S, there is another array, what does that do. So for the time being, yes, just 1 minute. Can you see it now? Okay. Sij is equal to k, and if then n for, we just close all this. So that's the entire algorithm. So I will not tell you what this S does for the time being. Ignore this. But write it now. Yes, there are n4. I didn't write all this n4. You write it at this point of the course. How many n4s and how many ndifs are required, I will not tell you. That should be automatic. Okay. Now let us see. You see the major change here. Previously this step was there. This is the crux. But this time it's not a recursive call anymore. M is a two-dimensional array. It's not giving any call. It's using this values. You kept these values at some point of time when you are calculating it, and then you are using it again and again, and that's changing everything. That is changing the entire complexity. Now let me tell you what is the basic method, what it is doing actually. Initially this is just an initialization, this step, nothing much. You are just putting all the diagonal elements of this two-dimensional matrix as 0, where you are keeping all these intermediate values. Now pictorially, roughly it means this L is running from 2 to n. So what it is doing, L will tell you what is the length of the matrices which you are trying to take care of now. How many matrices together you are trying to take care of now. So when L is equal to 2, what you are trying to do, you are just multiplying in pairs, each pair. That's what you are doing. When L is equal to 2, you can see I goes from 1 to n minus L plus 1, and J is basically I plus 1. It becomes I plus 1. So J, when L is equal to 2, the difference between I and J is exactly 1. So every adjacent pairs of matrices are getting multiplied when L is equal to 2, and that you are keeping in the two-dimensional array M in the proper location. So that is this 2. When L becomes 3, then it is trying to take 3 at it together, all possible 3 in a sequential manner. Now while doing this 3, it's doing the parenthesization in 2 possible ways. Suppose you have 3, 1, 2, 3. So either you can do this way or you can do this way. Now this way, this is already computed. The other also already computed and kept in the two-dimensional array M. So it's using those values and taking whichever is the minimum and keeping for these 3 what is the value. Okay, all possible 3 it's doing now. When L is equal to 4, it's taking sequence of 4 now. So when L becomes basically n, it has taken all matrices together and it has produced the minimum number of multiplication. Okay. So let us take an example to see how it is performing. So that will make things clear. So let us take the example. So here is the example. So suppose our matrices are, the array P is 4, 2, 5, 1 and 3. So it is the 0th index, 1th index, 2nd index, 3rd index, 4th index. So our matrices are like A1, A2, A3, A4. Okay, and this is the size. A1 is 4 cross 2, this one is 2 cross 5, 5 cross 1, 1 cross 3. We are trying to make an parenthesization. Okay, for the time being, we will not create the actual parenthesization. We will just count what is the minimum number of multiplications required, because that's what it is doing. M will produce that. But we will see very soon, using the other matrix, that is the S matrix, we can find out actual parenthesization. We will just see that one later. Let us understand first this one, the minimum number of matrix multiplication. How many minimum number of multiplications are required? Now let us see. In the now we have to go back to the algorithm. So initially our value L is equal to 2. So I just write here the values of M. So this is my M. One, two, three, 4. 1, 2, 3, 4. So all are initialized to be 0, the diagonal elements. So these are already 0. These are kept as 0. Alright. So initially L is equal to 2 and I is running from 1 to n minus L. What is n? Our n here 4. N is 4. So I is running from 1 to n minus L plus 1. 4 minus L is 3 plus 1, which is, so 1 to 3. 4 minus 2 is 2 plus 1. I is running from 1 to 3. So when I is equal to 1, so I 1, what is J? J should be 2. J should be 2. I plus L minus 1, J should be 2. So in that case, Mij is kept as infinity. So what is, so M12 is this location, which is initially kept it as infinity. Now let us look into the value of k. K is going from I to j minus 1, which is k is equal to going from 1 to 1, which is only once it will do. Mult becomes Mik. What is Mik? M11. M11 is 0 plus Mk plus 1j. Mk plus 1 is 22. M22 is again 0. So it is 0 plus 0 plus I minus 1 star Pk star Pj. What is that one? That is 4 times 2 times 5. 40. So basically that step is taking the first two matrices together and trying to see what is the total multiplications required. So that M12 is 40. So, and you can see if mult is less than Mij, that will update this infinity to 40. This will get a value of 40, right? Okay, so that is I is equal to 1, and then I becomes, because k that loop is done, k loop is done, then again I becomes 2, I becomes 2 and j becomes 3. So basically if you go over this again k loop, you will see it's trying to now multiply the matrices which is A2 and A3. It is trying to multiply A2 and A3, and again A2 and A3 will, so this is A2 and A3. So how much will that be, A2 and A3? It will be 10, and this will be 10 now, right? That is the k loop we will do. The next one again k will be done, I becomes 3, j becomes 4, j becomes 4.
So
Yes.
this one is mult less than
Yes, mult. So your question is, so I go back, right? Sorry. So he was confused with mult, how this got 10. Initially, see, we are putting infinity, and then 10 will be less than infinity, it will be updated as 10. You have to go back to the code. Okay, now let us see. I becomes 3, j becomes 4. So you are trying to see the multiplication of A3 and A4, and how much that will be. So basically you will get M34 as 15. Could you follow this step? So when L is equal to 2, basically see what you have done. When L is equal to 2, you have taken the A1 A2 multiplication, A2 A3 multiplication, A3 A4 multiplication, and we have kept these values. This is the minimum value. This is a very trivial one. There is nothing like minimum. 2 matrix multiplication, you know immediately how many multiplications are there. So you are putting those values, but you are keeping those values here now because you will reuse it again. So now our I loop is done. Now we will go to L loop. L becomes now 3. L becomes 3, and I now is moving from 1 to 2. I goes from 1 to 2. So when I is equal to 1, j this time should be 3. Is it 3? So I is 1 and j is 3, and k is running from I to j minus 1. So k is 1 to 2 running. When k is equal to 1, when k is, so now let us see, I know I know j, I know k. When k is equal to 1, look at this, mult is equal to Mik. What is Mik? 1 1, which is 0, Mk plus 1. So M23, but M23 already you have calculated, which is 10. So now 10 plus this Pi, what is that value? These 3 multiplications. 10. So it becomes 8. So 10 plus 8 is 18. So now we will update M ij, which is M13. So this will be 18. This will be updated as 18. See, when you did this AM13 as 18, what does it mean? It means you took the multiplication with k is equal to 1. So basically you multiplied the A2 and A3, then you multiplied this result with A1, and that gave you 18. Right? So this is 18 now. So k is equal to 1 is done. Now k is equal to 2. What is k is equal to 2 will give you? K is equal to 2, again MIK. MIK is what? M12 is 40. And then M22 is 0. 40 plus 0 plus that 3 thing, what is that? 20. So 40 plus 20, which is 60. Now you see, again this basically means you are trying to do update Mij, which was 18 previously, but now it is giving 60, so you will not update it. 18 remains. So pictorially what does it mean? Pictorially it means this. What did you do? A1, A2 and A3 was there. You first checked whether this one is better, which gave you 18. Then you checked A1, A2. When k is equal to 2, you check that one, A1, A2, and then multiplying this one, which gave you 60. And lesser one was kept. 60 is greater than 18, so lesser one was kept, which is 18. That's what this entire loop is doing. So this is k is equal to 2 done. So k is equal to 1 to done, and that means I is equal to, now I have to take I is equal to 2. When I is equal to 2, j is equal to, j must be 4. J is 4 now. So see, when L is equal to 3, we had to take 3 at together. So we took A1, A2, A3 already. Now we are taking A2, A3, A4. It is A2, A3, A4 now we are taking. And that's it. There are only two possibilities. You cannot take A3, A4, there is no A5. That's why it is varying like I going from 1 to n minus L plus 1. It's calculated properly. You have to keep at least L elements to the rightmost element to have these L elements. That's why the indices are running like that. It's very carefully designed actually. Okay, when I is equal to 2, j is equal to 4, again k is running from 2 to 3. K is running from 2 to 3. It must be 2 to 3. So when k is equal to 2, what are you getting? Tell me. When k is equal to 2, you are getting M22, which is 0, plus M34. M34 you must have calculated already, which is 15. 15 plus, tell me this 3 multiplication, what is that? So 30 plus 15. So 30 plus 15, which is 45. So I should get Mij. Mij is M24. So this one is 45. So it is updated because this is the first time it is getting updated. Infinity will be replaced. So that's fine. Now let us look at k is equal to 3. When k is equal to 3, Mik is what? M23. M23 is what? 10. 10, and M33 is already 0. So 10 plus this thing is what? 6. This must be 6. So 10 plus 6 is 16. Now 16 is less than this 45. So this will be updated now. So 45 will be updated and this will become 16 now. So what does this means? So this time you took A2, A3 and A4. First you checked A2 and A3, A4. That gave you how much? 45. Then you changed A2, A3, then A4 and that gave you 16. 16 is better, you kept 16. But you were keeping this one, you did not lose it. In previously also you were computing but you were losing it. This call, whenever you required, you giving another call. That was the bad thing. Now you are not giving another call, just using it. So now we are done. So let us see. Now we are in the last leg. So we are done with, so L is equal to now should be 4. When L is equal to 4, I is equal to going from 1 to 1. It should be 1 to 1. So I is equal to 1 to 1. J is equal to 4. J is equal to 4. So J is equal to 4 and K is moving from I to J minus 1, 1 to 3. So K is equal to 1 to 3. So let us see. When K is equal to 1, what is the thing? M I K. So M 1 1 which is 0, M K plus 1 J which is K M 2 4 is what? 16. 16 plus, tell me that one. 16 plus 16 plus 24 which is 40. So we get 40 here for K is equal to 1. Okay. Now K is equal to 2. What do we get? K is equal to 2. M 1 2 which is there. M 1 2 is 40. Then M 3 4 which is M 3 4 is 15. So 40 plus 15 already more. So let's not compute at all. It is already more. We will not do it. So let's take now K is equal to 3. K is equal to 3 means M I K which is M 1 3. M 1 3 is 18 plus M 3 3 which is 0. So 18 plus, tell me that one. It should be 12. It should be 12, right? So 18 plus 12 is 30 and 30 is less than 40. So we just update 30. And that's it. We have calculated everything and the minimum multiplication has appeared here. It's not 10. Minimum multiplication has appeared here, 30. Total number of minimum multiplication. It's not, oh sorry, don't do this. These were helping to calculate the ultimate one. Don't take the minimum. This 10 was just to compute the two matrices. But this is when L is equal to 4, you are taking care of the entire sequence. And there you took care of all possibilities and then you kept the minimum. So 30 is the minimum. And which gave the minimum? So I had A1, A2, A3 and A4. So I know when K is equal to 3 that gave us the minimum. So that means the parenthesization must have been like this first, right? All 3 were multiplied first, then A4 was multiplied because that's the last one gave that combination. Now A1, A2, A3 which gave you the better thing? Which for A1, A2, A3 that is A13. A13 is 18. Which gave you 18 actually? It was 2 3. So that was the parenthesization. So this is the entire parenthesization now. You know now that this is the one which gives you the minimum number of multiplication. Okay, have you understood this entire process with this example? Okay, now let us go back and now I will explain why we were using the another double dimensional array S. It should be clear by this time to you. Yes, right, exactly. So you look at this S now. Look at this S now in this algorithm. every time you are doing this Mij is equal to mult, that means you are updating the value of Mij. What you want to keep track that which value of k where you are cracking it, which gives you the minimum. That's what ultimately needed to produce the actual parameterization, and exactly that's what you are doing. Sij you are putting in k. So whenever you are updating Mij, that time you are putting the value of k, so that it tells you where you are cracking this sequence Ij. So once you remember that one, finally you can reconstruct this entire parameterization. So if I draw with this Sij, the value of Sij, let me just tell you, the value of S will be like this, with this example. Where did you say S12, this will be basically, if you see, it will be 1, and this will be 2, this will be 3. They are very not uninteresting case, because S12 is basically 2 matrices, there is nothing to crack. So k is equal to basically 1, here it was 2 3, k is 2, it was 3 4, k is 3, it's taking the lower one. Okay. Now comes when we are considering A13, we cracked at 1 basically. Remember the minimum, the 18 was given by the one where you are multiplying A23 first, then A1. So you put 1, you cracked at 1. Similarly, when you are doing A24, you cracked at what? When you are doing A24, you cracked at 3. You cracked at 3. Because 2 3 you were multiplying, then 4 was coming. Okay, then when you are considering A14, you cracked at 3. You first multiplied the 3 together, then you multiply, because the last k is equal to 3 gave you the least one, minimum one. So S is produced like this. Now given this S, can you come up with the parameterization? How can you use this matrix to come up with the actual parameterization? You have to write that algorithm. What do you do? It's a recursive call you can give. You first look at S1n. You know S1n, whatever value is that one, that will give you the first cracking, where the first division is done. So suppose it is 3, you immediately know I have to look at S13, and there is 3 to 4. 3 to 4 there is nothing actually. 3 to 4 is 3 basically. So that will give you 3. So M13 now will give you, M13 will give you 1. So you know that one is cracked at 1. So you have to go back in recursion and produce the parameterization. So I give you this one as an exercise. Once you have produced this array S, how can you use this array S to produce, to print out the actual parameterization? Write the recursive call. I just told you how to use it, but you should write, you should be able to write it properly using recursive calls and using this array, this double dimensional array S. Produce the actual parameterization. All right. Now let us see how much time was there while calculating. How much time did we spend to calculate this? How much time did we require? This is definitely of, this step is order of n, no problem. Now here this loop is running almost n. This is also running almost another n. Then again here there is another roughly n. So there are n times n, which will give you order n cube. You may think that it is not actually running n. Why am I taking n? But even if you count it exactly, you cannot save this n cube thing in this case. But you should not believe. First, you should not believe that you should take n. I told you, but you should not believe that first. You should verify that if I do it very carefully whether I can improve it or not. Since I know, I am telling you, even if you try, you will not be able to improve better than n cube. But you should try first. For any algorithm, don't take it pessimistically. Okay. So this will be your time complexity, and how much space does it take now? What is the total space complexity now? Order of n square, because we are using two matrices. We are using two matrices to keep track of all these values, intermediate values, and since it is n cross n, that will be order of n square. So in n square space and n cube time, you are solving this optimization problem. Previously, both of them were exponential, but by just keeping the intermediate value somewhere, we saved a lot of time, lot of space, and that's the major theme of designing and analyzing algorithms. Why one should study design analysis of algorithm? This is a perfect example. If you don't design algorithm properly, you will be spending unnecessarily. Probably you will not solve this problem at all. Practically, you cannot solve this problem. Okay. So this is just a perfect example to tell you that. Now, I was telling this, that even if you try to do it carefully, the analysis, you cannot do better than n cube. It's like this phenomena. Suppose you are doing a loop, the first loop is doing 1, second loop is doing 2, third loop is doing 3, it goes up to n. So what I said, I could have replaced each one as n and roughly is n square, which is right, that is the case, because even if it is 1, 2, 3 up to n, this is n minus 1 over n times n plus 1 over 2, which is order n square. So this is the phenomena. This will also happen if you try to do it carefully. Even if it is less here, 1, 2, but ultimately it gives you the same thing. Order wise it is same. Okay. Okay. So that completes the dynamic approach for this matrix multiplication chain. Okay. Now let me just take another triangulation algorithm, sorry, not triangulation, another dynamic programming problem where I will approach the dynamic programming approach. Okay, I will just tell you what the problem is, and in the next lecture I will tell you how to solve it. Okay, so that you know what is the polygon triangulation. This is called the polygon triangulation problem. Okay, so what is a polygon? Everybody knows it, I guess. So a polygon is basically a region in 2 dimension where the 2-dimensional region is bounded by a set of edges, straight line edges going over some vertices. So here it is a polygon. So I have just drawn one polygon. Okay, assumption is no 2 edge cross. So it's a valid polygon. So these are called edges, these are called vertices. Now one problem, it's a very practical problem. Objects are sometimes represented within the computer as a polygon, 2-dimensional objects. Suppose you have been given a 2-dimensional object and we would like to triangulate this object. Why? Because triangulation gives simple pieces of the object. Triangulation means what? Means I want to break up this entire polygon into triangles. Okay, I am just drawing one. You can see each one is a triangle now. So entire polygon now is expressed as a union of these triangles, and these triangles, the vertices of the triangles are coming from the vertices of the polygon only. You cannot use any more vertices. So this is called the polygon triangulation. Now for a given polygon, many triangulation may be possible. Like instead of, I am just giving you one example. Suppose instead of using these 2 edges, I could have also used this edge and triangulated that this way. There are many triangulations possible for one polygon, and one can show again, if the number of vertices of the polygon is n, the total number of possible triangulation again is exponential. Now suppose among all possible triangulation somebody wants to optimize something. Suppose I want to optimize, say, area of the triangle. So among all, you just given a triangulation, look at the maximum area of a triangle. Okay. Now among all possible triangulation, each one will return a maximum area of a triangle. Now you minimize over all possible triangulation that area. So you first you take the polygon, take a triangulation. That triangulation you just compute over all triangles what is the maximum area triangle. Alright. So each triangulation always gives you one value, maximum area triangle. So you have exponentially many triangulations. Over all possible triangulations, you take that triangulation which minimizes that area. I can change the metric also. Suppose I say take for a triangulation, take the metric as the maximum edge length of the triangulation. And over all possible triangulation, come up with the triangulation which minimizes that edge length. Several like this, I can produce several of such criteria. Like I can say what is the angle criteria. You take the triangulation, say what is the maximum angle over all triangles. That's the value of the triangulation. Now we say minimize that angle over all possible triangles. So changing metrics, you will be changing your problem. But we will see this entire problem can be solved using dynamic programming approach very nicely. Again in cubic time, in polynomial time, and we can just use almost any other metric. So the choice of metric will not matter. The technique is so powerful, metric you can replace it, only while computing you have to compute it differently depending on your metrics. So this we will see in the next class. How can we use our dynamic programming to solve this problem? You also think it over a little bit so that if you can come up with the solution. Now you know the dynamic programming technique. So try to see how can you apply the dynamic programming technique to solve this problem. It will be very nice to come up with your own solution. And we will see in the next class how to solve it using the dynamic programming approach.